So now we're going to go through a small numerical example. And clearly, the scale and the scope does not illustrate the entire TDP's generality, but it suffices to illustrate some of the key points in formulating one module in the overall schematic, that is the price optimization. So I'm assuming all the other modules are already well done and only focus on price or equivalently price reduction or reward optimization in a very simple formulation. Okay. So suppose we have just two periods, okay, night and day. And then suppose that on a particular training, we saw that there are two classes of usage: email and file download. Let's say email and file download, which could be, say, a movie download from iTunes. And email is a representative of the delay intolerant traffic, and this is file download, a representative of delay tolerant traffic. And suppose at night the total capacity demand is 300 megabyte from a small pool of users in the neighborhood. Okay. And 200 out of that 300 belongs to email. And the one remaining 100 megabyte belongs to file download. And during the day, you also have 200 megabyte of email, and then now, however, 200 instead of 100 megabyte of demand of file download. So during nighttime, you have a total of 300. During daytime, you have a total of 400. And let's say the current maximum capacity supported is 350, represented by the blue dotted line. Now, clearly, at nighttime, it is underutilized, and during daytime, it is overutilized. So we'll like to see if we can dump some of the daytime traffic to nighttime traffic, and ideally stretch the line to a straight line. In this particular simple example, numerical setup, such a straight line ideally would be exactly 350. Okay. So the question is, you have to provide some incentives through whatever user interface and pricing marketing plan, so that some of these traffic will flow from daytime to nighttime. Okay. Let's say during nighttime you offer certain reward, okay, reward denoted by P sub n, and during daytime you offer P sub d, n for night, d for day. Now you expect intuitively that the P sub n should be 0, because you actually don't exactly need incentive for traffic to move away from night into the day, but for generality's sake, let's give that a symbol. And P sub d you think would be some strictly positive number, you just don't know exactly what that number is. Okay. So let's assume that the ISP charge users on the $10 per gigabyte basis, okay, or 1 cent per megabyte, and the cost incurred for every gigabyte of capacity overshot is, let's say, $1. For example, representing the cost you need to roll out a truck to answer customer complaint, or the consumer churn rate cost, or the part of the cost for delivering higher capacity through expansion plans. Whatever the cost, let's say this is $1 per gigabyte for every gigabyte of exceeding the capacity. For example, during nighttime, before TDP, there is no cost of exceeding capacity. During daytime, however, there is 50 megabyte of overshot. Okay, so that's the setup of this problem. Now, our optimization variables are clearly P sub n and P sub d. That's two simple scalar variables in this numerical example. Now, what we have to do is to understand the expected amounts that will be shifted. Okay, let's say email and file download are going to have a very simple weighting function, actually simpler, much simpler than even this p over t plus 1 to the beta. Let's say it's simply proportional to the price. So nighttime, let's say email, so probability of shifting a unit of traffic, simply the price p offered over 4. And for daytime is PD over 4. Okay, for file transfer, it is more delay tolerant, and therefore the probability of shifting unit traffic is P sub n over 2 during nighttime and P sub d over 2 during daytime. So the fact is divided by 4 versus by 2 is representative of the fact that file download is more delay tolerant than email. Again, this is a very simple linear assumption here. So now we can write down the following, that for email, the amount that shift into nighttime, okay, is simply 200 units times Pn over 4. And the amount shift into daytime is simply 200 times PD over 4. And for file transfer, the amount of shift into nighttime is 200 Pn over 2 now. Okay, so this, and then the amount shift into daytime is simply 100 PD over 2. PD over 2 because of this factor, and 100 because it was 100 unit to start out with. Okay, 100 unit during nighttime. So the amount that can be possibly shifted into daytime has a basis of 100 units. So now that we have this table, we can easily calculate the expected amounts shifted into the nighttime and into the daytime. Now, since it's a binary simple example with 2 different time slots, of course, whatever goes into nighttime must have come from daytime. Whatever goes into daytime must have come from nighttime. That simplifies the derivation. So now we can express the following. Okay. The cost of reward is simply the following. For nighttime is the unit reward Pn times the amount of reward, amount of traffic expecting reward. Okay, what is that? I'm simply adding these 2 terms here. Similarly, I'm going to add up these 2 terms and multiply by the daytime reward. Okay, you can expand this, and it is 150 Pn squared, because Pm times Pm plus 100 Pd squared, because there's Pd times Pd. So it's a quadratic expression in the variables P and Pd for the cost of handing out reward. So let's remember this term, and this will be in the expression of the objective function. Okay. The other term in the expression of the objective function is cost of exceeding capacity, which we said is $1 for each gigabyte. Now let's look at the amount of traffic here. So amount of traffic shifted into nighttime from the previous table is simply the following. Equals 150 Pn. Okay, and amount of traffic that shifted into daytime coming from nighttime, that is simply the following. I'm just rewriting the expressions we just found from that table 2 slides ago, which is 100 PD. Okay, so you add up these 2 terms. Well, I should say you subtract this term from this term, because this is the amount shifted into nighttime, and this is the amount shifted to daytime, that is away from nighttime. This is into nighttime. Okay, so the original nighttime traffic is 300 unit plus 150 Pn is the amount you go into, and then minus the amount going out, minus 100 PD. And then you subtract the capacity you have, which is 350. This entire expression, therefore, is the cost of exceeding the capacity during the nighttime. And more strictly speaking, we should say this expression or 0, whichever is larger. So just in case this expression becomes less than 0, you just take 0, because you can never allow negative amount of traffic. Now this whole thing is for nighttime. You can write down a similar expression for the daytime, which turns out to be the max of 50 minus 150 PN plus 100 PD. The 50 is again 300 minus is actually 400 minus 350 for the daytime. And of course, the daytime, nighttime shift in and out are just exactly mirror image. Okay, whatever gets into nighttime comes from daytime. Whatever gets out of nighttime goes into daytime. And you have to make sure that it's positive. So now you've got this term and this term. You can put them together. That's the total cost of exceeding capacity. So let's assume that this cost, the sum of these two terms, and this cost are equally weighted. Then you just add up the whole thing together and you have the following objective function. It is 150 Pn squared. I'm simply writing down what we already derived in the last two slides. That's one term, okay, plus another term, which is the cost of exceeding capacity at nighttime and the cost of exceeding capacity during daytime. That's the entire objective function, and you would like to minimize this objective function with the following variables. Simply two scalars, Pn and Pd. As you can see, this is not a smooth function because of the max operation, but it is a quadratic convex function that you're minimizing over, and therefore it is a convex optimization. Well, in any case, it doesn't quite matter because it is only a small problem with 2 degrees of freedom. Again, the price setting varies P and PD. With a given P and PD, consumers will react differently, and the reaction will in turn drive the optimization. You can do it iteratively, or you can do it in one-shot optimization, and by incorporating the anticipated reaction from the consumers. Where's that? Well, that's all modeled in a simple way here with these terms. Okay, that's the expected amount probability of shifting for each unit of existing traffic. So with that incorporated into the objective function, we can solve this problem in one shot over these two variables. And you see that the resulting Pn star is actually 0.33 and Pd star is 0 indeed. Okay. You should provide no incentive for traffic to go into daytime. That's what Pd denotes, and the optimized value is indeed 0 because daytime is already overcrowded. Whereas you should provide some strictly positive rewards for shifting traffic into nighttime. That's what Pn represents, and the optimized value Pn star is 33. That is, you should discount the price from $10 a gigabyte down to basically $6.67 per gigabyte for nighttime. And if you induce, look at this, the induced traffic is exactly 350 units for daytime and 350 units for nighttime. That is, we achieved the ideal target of shifting just enough, 50 megabyte from daytime to nighttime, and therefore straightening this line over a 24-hour period and exactly meeting the capacity. That is more like an artifact of this particular numerical example. In the advanced material part of the lecture video, we will talk about a more general, even though not the most general still, formulation of price optimization. And remember, this is only one out of many, at least 5, depending on how you count, modules required for TDP to work. In advanced material, we'll also be talking about Paris Metro pricing, a very smart idea to charge different prices and then induce different quality of service, as well as a brief introduction to two-sided pricing, or this generalized 1-800 number for mobile data traffic. So before the advanced material part of the lecture, I would like to summarize what we have covered. In this lecture, we highlight that SDP smart data pricing may create win-wins across consumers, that's you and me, ISPs, and content providers. In particular, charging based on when is a very powerful idea used in many different industries. In mobile data industry, it may help time shift traffic through peak valley cyclic fluctuations. And across the last 2 lectures, we have seen a suite of ideas and models and design methodologies for mobile, or more generally internet data, especially data access pricing. And this is one big part of network pricing, together with what we already talked about, such as auction methods and other kind of ways to internalize negative externalities, and together with future topics such as fairness of allocation. These constitute our discussion on the economic side of network behavior. Now, we have talked about internet many times, including internet access pricing in the last 2 lectures, and the overlay network, including Wikipedia, including Netflix, including Google, Facebook, Twitter, on top of the internet. So what is the internet? Okay, it is a network of networks. And what kind of protocols control this network of networks? That will be the subject matter in the next sequence of lectures, starting with the basic foundational ideas behind the design of internet for our next lecture. So see you at the next lecture.